In the last class, I started talking about this math lesson, right, of variational calculus. That is, how do you minimize a function of a function? And so I made up this cute little example of a bobsled race where someone is trying to get from the beginning point to the ending point as quickly as possible, right? And there are different considerations, right? So you might want to take the shortest possible distance, like that. Or they might want to go down in the valley so they can pick up speed and go at the highest possible speed. Right? And maybe that would help them to reach the endpoint as quickly as possible. So let me remind you of how we got started with this calculation, and then I can finish it off. So to begin this calculation, and this is all just a copy of something from your notes from last time, I made up this expression for the travel time, right? That is, if you have the function y of x for the path chosen by the racer, then this integral gives an approximation for the travel time. And I didn't derive it all in class, but that's derived in the text. And then we said, well, what if we don't have just the path y of x? What if we have a slight change in the path? So instead of y of x, we go to y of x plus delta y of x. All right? And so in place of the function y of x, which goes here and here, we write y of x plus delta y of x. So that makes this expression right there. Okay, and then I expanded everything. That is, just multiply out these squares. And then I organized the terms based on what power of delta y each term has. Okay, so this first line is for terms that have 0 powers of delta y. So this is just the original travel time before I made the change in the path. And then this second line is terms that have 1 power of delta y. Those are what we're going to concentrate on. And then the last line is terms that have 2 or more powers of delta y. Well, just 2 in this case, but it could be 2 or more. And these I'm calling higher order terms because these are small when delta y is small, right? When delta y is small, then anything involving delta y squared is even smaller. So those terms are negligible when we consider very small changes in the path. So I'm going to neglect the last line, and I'll say the first line, that was just our old travel time. So what we really care about for the change of the travel time is this middle line. So already talked about that last week. And so this is the equation here for what is the change in the travel time. All right, so if we make a little change in the path, delta y, we get this expression for the change in the travel time. All right. And I wanted to say that this expression would be an integral of something times delta y of x integrated dx. The first term looks just like that. Great. The second term unfortunately does not look like that. The second term, it doesn't look like something times delta y, it looks like something times the derivative of delta y. Well, so in order to put it into the form that we want, did this integration by parts calculation. All right, and so you remember that from the end of the class last time. And so at the end of the integration by parts, this term transforms into this. That is to say, through the integration by parts, we move the derivative from the delta y of x to the y of x instead. And we get an overall negative sign. Okay, so now we got the travel time into just the form that we wanted. That is, it's an integral over all x of something times delta y of x. So then we can take whatever goes in this place, multiplying the delta y of x, and we say that is the functional derivative of the travel time with respect to the y of x. So functional derivative is the word for this thing. And so it's a generalization of the regular derivative that you learned about in your first year calculus course for a function of one variable, or the partial derivative that you learned about in multivariable calculus for a function of 2 or 3 or any discrete number of variables. Here we get the same kind of concept for a whole path y of x that can change everywhere over the whole range of x. So now we say we want to make up a criterion to judge whether y of x could possibly be the best path, right? Could it possibly be the path that gives the minimum travel time? Right? Well, the only way that it can be the minimum is if any small change gives the same travel time, right? Because if a small change gave a lower travel time, you should do that path instead. And if a small change gave a higher travel time, then you should make the opposite change and get a lower. Okay. So the only way we can have a minimum is if this functional derivative is equal to 0. So yes, we want this. So another way of saying this, we want this variation delta t to be 0 for all small changes delta y. So we want this functional derivative to be 0 for all x, right? This is an equation which depends on x, and we want it to be true not just at one position or two positions, but everywhere. The same way that if we calculate partial derivatives and we want to minimize a function of 3 variables, we want all the partial derivatives to be 0, not just one of them. Okay, so here then is the expression for what is the functional derivative. So we want this thing to be equal to 0 for all x. Of course, we can cancel this constant factor out in front. And so we would say we need the second derivative of y with respect to x to be equal to this constant times y everywhere for all x, right? So this is a differential equation, right? And so now we have derived a differential equation which must be true everywhere, and that's a necessary condition to have a minimum. So in any variational calculus problem, when you reach this point, right, when you derive the equation which says functional derivative equals 0, that is called the Euler-Lagrange equation for this problem. Okay, so here, the Euler-Lagrange equation for the bobsled race is this expression right here. Now, we still have to solve it, right? We don't have the solution yet. So we need to solve this differential equation using whatever is your favorite method for solving differential equations. My favorite method is guessing the answer, right? And so I want to say, is this differential equation similar to any other differential equation that I've ever seen? Well, here, this differential equation says that the second derivative is equal to a constant times the function itself. Okay? And in this case, it is a positive constant because all of the numbers here are positive numbers. Okay? So if we had an equation where the second derivative is a negative constant times the function itself, then we know the solution would be sines or cosines, right? But if it's a positive constant times the function itself, then the solutions are exponentials, right? Either an exponential of something times x or an exponential of negative something times x. Okay, so the easiest way to do this would be to say, let's give this constant a name. I will call it 1 over xi squared. Okay, so this Greek letter, it might or might not be familiar to you. This Greek letter is something that we write as xi, and American physicists pronounce this as xi. I don't have any idea of how Greek people really pronounce it, but let's just go with that. Theoretical physicists usually use this symbol to represent a length in a problem like this. And here you can see from dimensional analysis that xi must be a length if this equation is correct, because here this is a second derivative, right? So it has units of y divided by x squared, right? And over here on the right side of the equation, here's units of y, so this better be divided by length squared, right? So the equation can only be correct if xi is in fact a length. And if we go back and refresh our memory about what are all these parameters, energy, mass, gravitational constant, curvature of the valley, then yes, this is in fact a length. Okay, so if we want to solve an equation of the form d2y dx squared is equal to positive 1 over xi squared times y of x, then I recognize that the solution is that we could have y of x as something times e to the x over xi plus something times e to the minus x over xi. And these are two arbitrary coefficients. Let's give them names. Let's call them C1 and C2. Okay. So let's check if I got that right. Okay, so the first derivative, dy dx, is C1 over xi e to the x over xi plus, well, I get a negative sign from taking the square root. So minus c, not from taking the square root, from taking the derivative, excuse me, minus c2 over xi e to the minus x over xi. And then the second derivative, d2y dx squared, is c1 over xi squared e to the x over xi plus c2 over xi squared e to the minus x over xi. And sure enough, this is 1 over xi squared times y of x. Okay, so that's good. Okay, so this is a solution of the differential equation for any coefficients, C1 and C2. So then we say, well, how can we determine the coefficients? And the answer is from boundary conditions, right? That it's not enough to solve the differential equation. We must also include the boundary conditions in order to get C1 and C2. So let's go back to the original problem to remember what the boundary conditions are. So here is my picture, okay? And so the boundaries are at the starting point and the ending point, right? And so at the starting point, we would say if x is negative x0, then y is y0. Okay? And at the ending point, it's if x is positive x0, then y is y0. Okay? So we have to put both of those boundary conditions into the equation. So let's do it. Okay, so we have that y of x is c1 e to the, not minus, e to the plus, e to the x over xi plus c2 e to the minus x over xi. So I'll plug in x0 and negative x0. Okay, so y of x0 is c1 e to the x0 over xi plus c2 e to the negative x0 over xi, and that has to be y0. Okay, and y at negative x0. Let's see, what do I get there? It's c C1 e to the negative x0 over xi plus C2 e to the x0 over xi. That's also equal to y0. Okay, how do I solve this? Well, this is two equations in two unknowns, right? C1 and C2. Okay. So I could do something like adding or subtracting the equations. How about if I subtract them? Okay, so if I subtract them, let's see, it's C1 times e to the x0 over xi minus e to the minus x0 over xi plus C2 e to the minus x0 over xi minus e to the x0 over xi equals 0. So C1 minus C2 e to the x0 over xi minus e to the minus x0 over xi equals 0. Okay, so xi, you remember, is some combination of all the input parameters, the mass and the gravitational constant and so forth. X0 is something about the length of the race, right? And it's not 0, right? The race has some length, it's not 0. Because x0 is not 0, this thing is not equal to 0. So I'll divide both sides by it, and I get C1 minus C2 equals 0, right? So C1 equals C2. Okay, so then I'll go back and plug that into one of the equations, like here. Okay, and then I get what? C1 times e to the x0 over xi plus C2, which is the same as C1, e to the minus x0 over xi, right, equals y0. So C1 is y0 divided by e to the x0 over xi plus e to the minus x0 over xi. Okay, so that's C1 and C2 is the same thing. All right, so let's write out the equation, the final answer, sort of neatly. Okay. So that would be y of x is this overall coefficient, y0 divided by e to the x0 over xi plus e to the minus x0 over xi. And then that is all multiplying e to the x over xi plus e to the minus x over xi. If you remember your hyperbolic functions, then there could be a shorter way to write this thing. All right, so if you remember that the hyperbolic cosine is, which is written as C-O-S-H, and it's pronounced cosh. This is e to the x over xi plus e to the minus x over xi divided by 2. And so with this handy hyperbolic function, we get that y of x is y0 times this hyperbolic cosine of x over xi divided by the hyperbolic cosine of x0 over xi. So here's our answer. Okay, so if you're familiar with hyperbolic functions, it's nice and compact. If you don't remember hyperbolic functions, of course you could write it out as exponentials. It's just a little bit more writing. But hyperbolic functions are nice to know about, and they're not that exotic. They're available, on the iPhone calculator app and in Excel and places like that. Okay, so what can we make of this, right? Well, there are a few things to do when you get this solution to a problem like this, okay? So one thing that is always good is to check, wrong pen, check that it solves the differential equation. Or maybe a better word, I'll say, check that it satisfies the differential equation. That is, if you take the derivative of your final answer, right? Does it agree with the differential equation? That's good, okay. We can check that it satisfies the boundary conditions. That is easy in this case if you happen to remember hyperbolic functions, because then you could just plug in x is x0, and then the numerator and the denominator cancel, and you just get y0. Or if you remember that the hyperbolic cosine is an even function, then if you plug in x is negative x0, then you get the same thing in the numerator, and it cancels the denominator, and you just have y0. Great, okay. What else could you do? Well, you can plot it. Okay, so you could plot y of x as a function of x from negative x0 to positive x0. So if you remember hyperbolic functions, then you would know that the hyperbolic cosine increases like an exponential over here up until it reaches y0. Okay. And on the negative x side, it increases like an exponential over there until it reaches y0. So this is the shape, okay? If you don't remember hyperbolic functions and you want to go back to the exponential expression here, what would you do, right? Well, you'd say for large positive x, you have this exponential plus that exponential. And this is a really big number, and this is a really small number. And so for large positive x, it's dominated by this term. So it should look like an increasing exponential, right? And that's the trend over here. Right? And what about for large negative x? Right? Well, for large negative x, this is a really small number, and this is a really big number. And then the function is dominated by this piece, which is a decreasing exponential. And so you have this decreasing exponential. And then they come together here at x equals 0. Okay, and so this is a function that looks a little bit like a parabola, except that the curvature is really concentrated out there and there, and it's pretty flat in the middle. Unlike a parabola, which has curvature pretty much everywhere. Okay. And then what else could we do? Well, we can notice in what range is the curvature concentrated, right? So we can see that the function, let's look on the positive x side, right? It's increasing here, and the exponential increase is always associated with some length scale, right? That in the exponential factor like this, right, there's a characteristic length, psi, over which this term changes by a factor of e. Right? So an exponential does most of its increasing and decreasing over a certain limited range, right? Where the argument of the exponential varies by 1, so that x varies by psi. So that means that the change in the function, say from there to there, is concentrated over a length psi. Right? And similarly, on the negative x side, the change from there to there is concentrated over a length psi. Right? So we can interpret that, the way that the racer would think, right? The racer would say, I'm starting off up here, and I want to get down to the valley pretty rapidly, right? Get down to the valley over a length scale of psi. And then I stay near the bottom of the valley for most of the distance. And then I'll do my increasing again over a length scale of psi. So psi tells us what is the sharpness of the change, right? If psi is really small, then the change is really sharp. Right, you drop down quickly and then turn. Right? On the other hand, if psi is really big, then it's a really gradual change. You drop down slowly and then turn in the middle. And then, one more change that we could make would be to see about the limiting cases. That is, what if we change a parameter like the mass of the sled, okay, and say, well, does the change in the solution make sense, right, in terms of the mass of the sled? Okay, so where does the mass of the sled come in? Well, it comes into the number psi, right? So let's remember, what is psi after all? Okay, I defined it a long time ago and I forgot by now. Okay, so here it is, right? This is the reciprocal of psi. Okay, so I'll copy that. It's fast, I didn't copy it. copy. Okay. So if I remember what it is, maybe I'll put it up here. Okay, so this thing is 1 over psi squared. Okay? So that means that psi is the square root of 2e naught over mgk. Okay, so what happens if the sled is really heavy? Okay, so if the sled is really heavy, that is, if m goes to infinity, then psi is very small, right? Because m is in the denominator. Okay, so that means that if it's a really heavy sled, then it's really important to drop down quickly, right? Then you really want to get down to the bottom of the valley quickly so that you get the maximum gravitational boost in the speed, right? That the gravitational boost in the speed is really important for a heavy sled. What about for a really light sled? Okay, so if, on pen, if m goes to 0, right, then, well, m is in the denominator there, so that means psi goes to infinity. So if psi goes to infinity, then that will tell us that you don't drop down quickly. In fact, you don't really drop down at all, right? If psi is infinity, then you just, barely make any change. And then you finally, reach the middle of the race. So if it's a really light sled, then the gravitational boost in the velocity is not so important. It's really not important at all. And so you just want the shortest path. That'll be this one. So this is the kind of thinking that you want to do when you reach the solution of a problem, right? And when your student's taking a class, right, and the professor tells you a list of 4 extra things to do, you think, oh no, that's extra work. I've got to do all those extra things, man, right? But when you're doing research, you think the opposite way, right? When you're doing research, you think, oh, I really want to have a lot of ways to check my work, because it would be really embarrassing if I tell somebody I accomplished this research and it's wrong, right? And so when you're doing research, you want to have as many ways as possible to check your work and make sure it's right. And so it's good to have lots of checks like this. And so these are all good things to think about. Okay, so this is my cute little example of a variational calculus problem. And so we have now reached the answer. And this is the same answer which is plotted here at the beginning, because I solved it before I made this graph. And so this is a hyperbolic cosine function. That is this trajectory. But apart from the answer of this particular problem, what I want to emphasize to you is the method, right? Because this is the kind of method that we're going to use for other problems where we need to minimize a function of a function. Okay, and so the idea is that we always want to do this kind of procedure. That is, we always want to put in a little variation on our input function and see what that does to the output. Right? And then express the change to the output like this, okay, as an integral over our entire domain, whatever that is, of something times the change in the input function. And the something has to be 0. So the Euler-Lagrange equation is what says the something is equal to 0. That gives you a differential equation. Then you have to solve the differential equation using whatever is your favorite differential equation solving method. And then you get the answer. And then you have these various possible ways to check the answer. And so, yeah, there's a bunch of steps there, but nobody told you this was going to be easy, right? I mean, if graduate school were easy, then everybody would have a PhD, right? And so, these are the kinds of steps you have to go through. Now, there is one way that students sometimes remember this, and I will show it to you even though I don't love it, okay? So I'll say one possible way to memorize this procedure is to think back to classical mechanics. Okay, so remember when you were studying classical mechanics, well, I mean, if you were a physics major, you probably studied this. If you were coming from a different major, perhaps not, okay? But when you were studying classical mechanics, if you were a physics major, you learned about something with Lagrangians. Okay. Is this familiar to some of you guys that you saw Lagrangians somewhere? Okay. So you learned that there is a Lagrangian, L, which is the kinetic energy minus the potential energy. And people write this as T minus U, or T minus V, I guess. T minus V. Okay, so the Lagrangian equation of motion is to say that the derivative of the Lagrangian with respect to whatever is your coordinate, let's call it y, for example, if you have some y of t, okay, then the derivative of Lagrangian with respect to your coordinate minus d by dt of the derivative of the Lagrangian with respect to y dot, that is the velocity, is equal to 0. Okay, so this is an equation that may be familiar to some of you, right? If this equation is familiar to you, I am talking to you. If this equation is not familiar to you, go take a nap for 5 minutes and then come back, okay? if this equation is familiar to you, then I will point out that this equation looks just like what we just did, okay? That this equation, in this equation, we would say that the first part of the variation that we're doing here, wrong pen, the first part of the variation that we're doing here, this is like the dl dy part. The second part of the variation, that's like this thing, where this is negative the x derivative of the derivative of the function we're working with, the travel time, with respect to y dot. Y dot now means dy dx instead of dy d time. Okay. And that is not just a coincidence, but rather Lagrangian mechanics can be derived from the minimization of something called the action. The minimization of the thing called the action, which is the integral from the beginning to the end d time of the Lagrangian of time. Okay, so the this is sometimes called the principle of least action. That is, classical mechanics automatically minimizes this thing. Classical mechanics minimizes this integral, which is called the action. It minimizes the time integral of the Lagrangian. Maybe you ask, why does classical mechanics minimize the time integral of the Lagrangian? I'm not going to answer that one. There's some profound work of Richard Feynman, which is like a quantum mechanical explanation of that. But that is way beyond the scope of what I'm doing. But you can just take it on faith that classical mechanics minimizes this thing. And if you want to minimize this thing using the methods that I have shown you, then you get this equation, where this is the easy piece and this is the harder piece that requires integration by parts. And this then turns into an equation which is possibly familiar to you from a classical mechanics course. Okay, so for students who are learning variational calculus, if they want to memorize something, they might memorize an equation like this and say, oh, I know what to do. I'll take the derivative of the thing I want to minimize with respect to the function in question and subtract off this other combination of derivatives, and that gives the Euler-Lagrange equation automatically. You can memorize that if you want to. I don't love it because it just looks weird to me to think of these as separate derivatives when really they both come from the same variational procedure. They really come from the same idea of putting in a little variation of y of x and seeing how that changes the output that you care about. Okay, so if you really want to memorize it, you can, but I don't especially recommend that. what I recommend instead is just seeing what are the steps that you have to go through with the derivation that I've done for you. And, maybe it seems like a lot of steps when you first do it, but you get used to the sequence. And then after you get used to it, it seems sort of natural, and you can just, remember how it goes. It's like with everything else in life. When you do it a few times, you get used to it, and then you remember how to do it. So to help you learn this, I will say there is a new homework on Blackboard. So you don't have to thank me. I'm just a nice guy. I posted it there for you. So you can go take a look and see, and I made that due 1 week from today. So please go take a look, and that will be one variational calculus problem for you to practice with. Okay, so that wraps up my math lesson. And in the next class on Wednesday, I'm going to go back and apply this to physics and talk about the concept of a field theory. So that's in chapter 6 of the book. So please take a look at chapter 6, and I'll see you on Wednesday. But for now, I'm glad to answer any questions, of course.
Could you please explain a little bit more about the model of a bobsled? Because you told us that the optimal trajectory for the bobsled depends on the mass of the sled, right?
Mm-hmm.
If we think about a simple model like free fall, then I think the motion of an object for free falling doesn't depend on the mass of the object, right? So could you please explain the physics of how the mass of the slab plays an important role in this process? I mean, if the slab falls a certain amount of height, then no matter what the mass is, the gain in kinetic energy, the gain in the velocity is always the same, right?
Let me think about that for a second. The way, well, okay, I have two answers. Okay, and answer number one is that this is different from an object that's just in free fall under gravity in a vacuum, because here there's a racer who is choosing a trajectory in order to minimize something, right? It's not just like dropping an object and it falls however it falls, right? And so in the race problem, you're actually trying to minimize a travel time. In just natural falling, there is no principle of minimizing a travel time, right? There is a travel time, and the principle of least action is not a principle of least travel time. That's one answer, okay. Answer number two is this problem is designed with certain specific assumptions, which may not actually be great assumptions for a real bobsled race, but I'm not a bobsled racer. And it's designed with the assumption that there is a certain initial energy. Okay, and so back in all these equations, there's an initial energy here, which is divided by the mass.
Mhm.
Now, the initial energy is a combination of the initial kinetic energy, because the race is starting way up the hill, its initial potential energy from being way up the hill, and the initial kinetic energy because, maybe the sled has a moving start. Okay.
Mhm.
I did I did these limiting cases, assuming that I was changing the mass, but keeping the same initial energy. Okay. That might not have been the best choice for me, right? Because you might think if the mass is bigger, then the initial potential energy is bigger and the initial kinetic energy is bigger, right?
Mhm.
And so maybe it's kind of crazy to vary the mass without varying the initial energy, okay? I think that's the reason that what I'm saying is not agreeing with your intuition, right?
Okay.
And your intuition is probably pretty good, right? And so probably a better limiting case would be to change the other parameters, right? I could change
Yes.
gravity, or I could change the curvature of the valley,
Mhm.
right? So K is the curvature of the valley, right? So a big K would be a very steep valley,
Mhm.
right? And so maybe it would have been better if instead of saying big mass or small mass, if I had said big K or small k, right? And then I wouldn't have had uh, this problem of discrepancy between the math and the intuition, right? And so that is actually an excellent point that you're making. And so that example would have been better than the example that I actually gave.
Okay.
So I'll see if I can remember that for next time.